So maybe the burning question in your heart is, if strong acids can add across a double bond, what about a weak acid like water? Well, as you can see in equation 1213, basically no reaction occurs if an alkene is treated with water, that weak acid, under neutral conditions. With water as the acid, the first step of the general mechanism for that electrophilic addition of that Bronsted acid to an alkene is just too unfavorable to take place at a reasonable rate. Basically, it's just too slow, right? The first step not only would produce a carbocation, but would also produce OH minus, which is a strong base, and is also a negative charge and is relatively poorly stabilized. So it just doesn't work very well. Now, it turns out though, if you look at equation 1214 here, that you can add water to an alkene if you have a strong acid. And basically water is H2O, and OH adds to one carbon and a proton adds to the other carbon. And so you go from an alkene to an alcohol. And again, we have a functional group conversion here. So this is a reaction that you could use in synthesis to change the functional group. So let's look at the mechanism. Now this is called an acid-catalyzed hydration mechanism. And what we'll notice here, let me get my alkene drawn, is we have an alkene, and then you are going to see the acid shown as H30. We're going to show the water being protonated. So it's going to be H3O plus. So the acid protonates the water, and now we have H3O plus running around. And so when we look at H3O plus, those hydrogens are partially positive because the oxygen here is carrying a positive charge, and so it's sucking off that electron density as well as being very electronegative. And so we're going to see the first step here is that these electrons are going to come out and attack a proton, and those electrons are going to go back on the water. Okay? Now, what happens, so that first step is an electrophilic addition. Okay, and so now you have this guy with a positive charge there. Now notice Markovnikov's rule is still in effect. There are more hydrogens here, so that proton's going to go there. That leaves the carbocation for here. Now, even though water's a weak nucleophile, the reactivity of the carbocation intermediate compensates for that. It's going to react really fast. And the electrons on the oxygen are going to come and they're going to attack that partially positive carbon, and they're going to form a new bond, okay, in a coordination step. Then what you're going to have is we've attached that water, but now we have a positive charge. Another water molecule, because remember there's lots of water molecules running around in this solution, is going to come in and it's going to undergo a proton transfer step where it removes this, those electrons go there, right? And so you end up with your alcohol, okay? Now, one of the things to be aware of is we're adding water here, but remember, if you have H2O that looks like this, alcohols react very similarly to water, okay? Because all we've done is exchange a hydrogen for a methyl group, for a CH3 group, or another R group. So this same mechanism will work if you add an alcohol, okay? So if an alcohol were added, it's called an acid-catalyzed alkoxylation reaction. Okay, so if you add an alcohol, it's an alkoxylation reaction. This, if you add an alcohol, will produce an ether, right? Because when you add, if this is an alcohol, right, so just change this out for CH3. When you add that, instead of this hydrogen here, you have some sort of R group, and so you have produced an ether. So that's also a way that we can have a functional group transformation from a double bond to an ether is by adding an alcohol. Now, maybe your question here is, okay, I noticed on the previous slide, Dr. Pierce, that sulfuric acid was the acid catalyst, right? Can you use any acid catalyst? And the answer to that is no. You cannot use things like HCl, HBr, because those are strong bases that dissociate essentially entirely in water, right? That's the idea of a strong acid. And so, but HCl is generally not used because it can itself go through an electrophilic addition reaction, and you would not get the product that you were looking for. So for example, if we have ethynyl benzene, which is known as styrene, that's its common name, and we were trying to use HCl as our catalyst, what would happen, instead of adding the OH here, we'd end up with a Cl. So the HCl would add across here. So sulfuric acid tends to be the strong acid that's used. Sometimes phosphoric acid is, but you generally stay away from your other acids that can undergo electrophilic addition reactions by themselves. Now, we have talked a lot about alkenes, and maybe the question you have is, Dr. Pierce, I know that we can also have alkynes. Do they react the same way? And the answer is sort of. Like the carbon-carbon double bond of an alkene, the carbon-carbon triple bond of an alkyne is very electron rich. And so as a result, alkynes can undergo electrophilic addition reactions with strong Bronsted acids in almost the same way that alkenes do. When you have ethynyl benzene treated with a strong Bronsted acid like the HCl, an addition will occur, right? But you're left with a double bond, so you get a second addition, okay? Now, I want to point something out here. The reaction of the alkyne with the hydrogen halide produces something called a geminal dihalide. And in a geminal dihalide, when we talk about that, this is a geminal dichloride, but a geminal dihalide, right, has both halogen atoms on the same carbon. Okay, so both of those are on the same carbon. So that's a new vocabulary word that you need to know, okay, because that'll come up again. Let's look at the mechanism for this. So this is the electrophilic addition of an alkyne. When we look at this mechanism, we are going to start, and I'm just going to do the mechanism for the previous reaction. So there's our triple bond. We're going to add HCl. Those electrons are going to come out. They're going to steal that proton. Those electrons are going to go back on the chlorine. That's the electrophilic addition step. Okay, then there's a little stop in the screencast there. I had to pause the screencast for a moment. And I don't remember where we were. So we'll just kind of pick up where there was an electrophilic addition reaction. And now we get this product with a carbocation there, right? And then we've added the hydrogen to the other side of the double bond there. Now, this is called a vinylic cation where that positive charge is on the double bond there. What happens now is the chlorine ion that's running around is going to come back in and attack that carbon in a coordination step. Now, I'm just going to change it so that it looks a little more obvious there's a carbon there. So we have that double bond and a chlorine, okay? This can play again and go through another electrophilic addition step. Where these electrons come out, they steal that proton, those electrons go on the chlorine. What you're going to find here is that this guy is resonance stabilized. There is a positive. A resonance structure, and I'm just going to show the resonance structure down like this, where right, it would look like that. So there's resonance stability there. That's a very stable carbocation. It's not a resonance structure that's necessarily intrinsic, so I do like to point that out, but that is a resonance stabilized carbocation. This can go through coordination. Again, with another chlorine. Here. And when it does that, now you have your product. Okay. Now, the major product is the result of two additions, not one, because the second addition is easier than the first. And it's easier because that carbocation that's produced is more stable because of resonance. And so I want us to kind of make some notes about this. The second addition, right, is easier because, right, one, the carbocation is resonance stable or stabilized, right? Another thing is, there's an effective electronegativity difference. So the alkene carbon of an sp2 hybridized, when we have the alkene carbon, right, we have an sp2 hybridization. So it has a lower effective electronegativity here than the alkyne carbon, which is sp hybridized. And so it's going to handle that positive charge a little bit better here. Right, and so then of course, so that makes it favorable. That's not the reason necessarily the second addition is easier, right? But that is one of the reasons that this is a favorable reaction. So, two kind of things that help this be really favorable, but this addition is faster because the carbocation here is more stable and it's more resonance stabilized. I want to talk about this a little bit more on the next slide, I want to talk about bromine for just a second. So in this equation, the vinylic cation is resonance stabilized here, right? Because of that benzene ring, right? But hydrogen halides can add to alkenes or alkynes even when that resonance stabilization is unavailable. An example is shown here, right? The mechanism for this reaction is believed to be slightly different. So with the chlorine, we can get some of that resonance stabilization with that benzene ring. This still works, right? You need 2 equivalents of HBr, so we're going to have this in excess. But when this reacts, this produces a vinylic cation with a localized positive charge, and that makes the species really high in energy. And so what people believe is happening is that, or what they have proposed is to avoid that vinylic attack. Br here attacks a pi complex of the acid, so it makes this pi complex where it aligns this way to help stabilize it. This is something different. So, we talk about like how science changes. This is something that's been added recently to being taught, is that there's a belief here that there's some sort of stabilization that's occurring and there's some sort of pi complex, okay? Now, let's talk about acid-catalyzed hydration of an alkyne. So we can add chlorine across the hydrochloric acid across the double bond. We can add hydrobromic acid across the double bond. Can we add water in the presence of acidic conditions? And you can. Now before, when we did a double bond, we formed an alcohol, right? But I want you to notice the acid-catalyzed hydration of an alkyne does not form an alcohol, it forms a ketone. So this is a way we now have a way to synthesize ketones when we're looking at multi-step mechanisms. So let's look at the mechanism for this. So we've added acid, so we have H3O plus. These electrons are going to come down, they're going to grab that proton, those electrons are going to go back on that oxygen, okay? This is our normal electrophilic addition step, okay? Now, we have a double bond there with a positive charge, that's our vinylic carbocation. Water's going to come in. These electrons are going to attack that partially positive carbocation in a coordination step. Okay. Ooh, I left out the electrons there. Let me put those back in. Whoops. There they are. Okay. Now, we have OH plus. Okay, but I want you to recognize something. Well, we're gonna have a proton transfer, and then I want you to recognize something. So those electrons are gonna grab that proton, those electrons are gonna go on that oxygen. And now we have an OH, but what you should recognize is this is an enol. This is an OH next to a double bond. So this sucker can undergo tautomerization. And now we have a ketone, right? And that's the more stable ketone. So we've noted a few, we're going to talk about a few important aspects. The first important aspect here is the product's a ketone. It is not an aldehyde, so that's just something to kind of be aware of due to Markovnikov's rules, right? The second thing I want you to notice, and particularly on the previous slide, is the reactions run at really high temperatures. So the addition of the H plus in the first step of the mechanism produces that vinylic carbocation intermediate, and that intermediate's really unstable. So the first step has a large energy barrier when H3O plus is the acid, and one of the ways you can get over an energy barrier is by adding a lot of heat. So this is run at really, really high temperatures. Now, there are other things that we can do to increase the yield of an acid-catalyzed hydration reaction like this. And one of the things is that we can use a acid catalyst that's stronger than sulfuric acid. In this case, what you see here is trifluoro methane sulfonic acid, right? This is sometimes shown as catalytic TFOH, which is also known as triflic acid. So, triflic acid, okay? And that's in 2,2,2-trifluoroethanol, which is the solvent there, okay? And so we can use a much stronger solvent or much stronger acid to help increase the yield there, right? This is always comes with some risks. Sulfuric acid is already a pretty strong acid, and so you always want to make sure that you wear goggles and gloves and an apron and work in a hood because it's really strong. And so moving up to an even stronger acid than sulfuric acid just inherently leads to a lot more risks. So you do with these types of reactions a lot of times, the risk reward, you need to think about you need to do a risk analysis to decide if it's really worth it and how much of a gain in yield you'll get. And that's something you always want to think about when you're designing a reaction, right? Is are the materials that I'm going to use worth it? Price-wise, safety-wise, all of those things, right? So that's something that you always want to consider.